Yeah, welcome to the session 2 of the course Wireless Communication and Mobile Technology. So, the objective of this session is to introduce the various frequencies for radio transmission. So, after going through this session, the students will be able to understand the various frequency bands which is available for radio transmission or wireless transmission. They will be able to know the facts about signals, antennas, and signal propagation. And also, they will be understanding the role of multiplexing in wireless communication. Because in a wireless communication, the media is a shared media. The media is air, the open space. So here we need some multiplexing techniques for transmitting the signals without any interference. And then the students will be knowing the need of modulation to transmit digital data. Whenever you want to transmit a digital data, it should be modulated with the analog carrier, and then only it can be transmitted. So what is the need of modulation? That you will be able to understand. And also you will be getting the knowledge of spread spectrum and a brief introduction to cellular systems. So this is the objective of this particular session. So let us start with the frequencies, the band for radio communication. So these are the various frequencies available for radio communication, starting from very low frequency to infrared frequency and visible light and ultraviolet frequency. So these are the different frequencies available, and different frequencies were used for different types of communication. So let us understand which frequencies were used for which communication. Here you can see many terms like VLF. Uh, so VLF represents very low frequency. LF represents low frequency. MF means medium frequency. HF is high frequency. VHF is very high frequency. UHF is ultra high frequency. SHF is super high frequency. And EHF is extremely high frequency. So these are the different types of frequencies which were used for different types of communication. That will be understanding like which band of frequency is used for which type of communication. Okay. So the spectrum of data transmission, it varies from 300 hertz to 300 terahertz. So you can see here the starting is 300 hertz, and here the visible light spectrum or UV spectrum, it is in the range of 300 terahertz. So basically the relationship between frequency and wavelength is given by this equation. Lambda is equal to C by F, where lambda represents the wavelength, and C represents the speed of light, and F is the frequency. So yeah, so here C is a constant which is 3 into 10 to the power 8 meters per second. So these are the different frequencies which we have already discussed in the diagram. So there are around 9 types of frequencies, and different devices or different communication means were possible through various frequencies. So let us first start with the traditional wired networks. In a traditional wired networks, for communication up to several kilometers, around 100 kilohertz of frequency, the signals with several hundred kilohertz signals were used. And typically these signals, they use coaxial cable. they use coaxial cable. So coaxial cable can support a maximum signal with a frequency of several hundred kilohertz. And then comes the twisted pair cable, which supports signal with frequencies of several hundred megahertz. And then we have optical cable, fiber optics cable, which supports signal with frequencies of several hundred terahertz. So this is about wired networks. So our concentration is on wireless communication, radio transmission. So VLF represents very low frequency. These are long waves. If the frequency is low, then the wave will be long. If the frequency is less, then the wave will be shorter. Okay. So the application of VLF is not much. So let us start with low frequencies. So low frequencies were basically used by submarines. Low frequencies were basically used by submarines because it can and penetrate through water, and also it can penetrate through the earth's surface. And then medium frequencies and high frequencies. Medium frequencies and high frequencies were basically used by radio stations for using AM and FM transmission, that is amplitude, using amplitude modulation and frequency modulation. For amplitude modulation, it works in the frequency between 520 and 1605.5 kilohertz. And for frequency modulation, it works in the in the bandwidth of in the band of 87.5 and 108 megahertz. Okay. And there is also another type of radio communications which is called as short wave radio communication, which operates at a frequency of 5.9 to 26.1 megahertz. Okay. This also comes under the comes in the range of medium frequency or high frequency. Okay, so basically it comes under high frequency because medium frequency is less than 3 megahertz, so it is more than 3 megahertz, so it comes under high frequency signals. Okay. So this shortwave radio is used worldwide, and how it works in the sense it works by reflecting through the ionosphere. That is, these waves cannot pass over ionosphere, so it reflect back and forth between the ionosphere and the Earth's surface, and by that it transmits over the world. So so it can so it means it can transmit throughout the globe. And then we have VHF, very high frequency. Uh, so there is analog TV operating on very high frequency in the frequency band of 174 to 230 megahertz. And followed by that, we have UHF, ultra high frequency. Here also we have analog TV operating in the band of 470 to 790 megahertz. So there are several devices which is working in the ultra high frequency band, and there is also digital TV which is working in UHF, ultra high frequency, in the frequency band of 470 to 862 megahertz. And then we have DAB in ultra high frequency, digital audio broadcast, which is available in two different bands, 223 to 230 megahertz, and also from 1452 to 1472 megahertz. And also there are mobile phones with analog technology also operates in ultra high frequency in the frequency band of 450 to 465 megahertz. And then we have GSM, which is also working in ultra high frequency in the band of it works in two different bands, 890 to 960 megahertz, and also 1710 to 1880 megahertz. And again we have digital cordless telephones which is also working in ultra high frequencies in the band of 18802 to 1900 megahertz. And 3G cellular systems are also working in UHF, ultra high frequencies, in these bands 1900 to 1980 megahertz to 2020 to 2025 megahertz and 2110 to 2190 megahertz. And then we have directed microwave links, which is working. These are basically super high frequencies, which is working in the bandwidth of 2 to 40 gigahertz. Followed by that, we have infrared, which is we have EHF, that is extremely high frequency, which is close to infrared frequencies. Okay. So these are the different frequency bands and the various devices which is operating in these different bands. Okay. And the next step in higher frequencies, that is in future, probably what we will have in the sense, optical transmission, mm, wireless communication may be possible through optical transmission also. Okay, that is uh, optical transmission for wireless communication will be introduced, and also infrared transmission can also be used for direct links, that is for connecting different buildings through laser light. This is a typical example. Okay. So why we are discussing about these frequencies? Because in if you take wired communication, then there is no issue of frequencies, because you have a wire, and the communication happens through that particular wire. So there is no question of interference. There is no question of interference. The signal is focused in one particular direction, and the signal is protected by the shield of the cable or wire, whatever it may be. Okay, so the chance of interference is very low. In wired communication, also interference may happen if this wire is getting crossed by another wire which is operating at a very high frequency. In that case, there is a possibility of interference, but otherwise, generally, there will not be any interference. But this is not the case in wireless communication. In wireless communication, the media is a shared media. So different devices, uh, will, everybody is using the shared media. That is, air is the media, and so everybody cannot work in the same frequency. If everybody works in the same frequency, then there will be a lot of interference, and the communication, whatever the sender wants to send, it cannot be received by the receiver. So there should be some standardization done, like uh, which frequency should be used by whom and like what. Okay, so that is the reason why we are very much particular about these frequencies. And generally, these frequencies were allotted by some international or national standards. So they define like who should use which frequencies and for what purpose. So that's it about the frequencies of for radio transmission. So next, let us try to understand the properties of wireless signals. Okay. So basically, signals are used to represent data. So signals are nothing but it is one way of representing data. So through a wireless communication media, either you may talk or you may send some information like a text message or whatever it may be. All these are sent as signals. Okay. So finally, but these signals represents data. So signals are nothing but physical representation of data. That is what is a signal is. And signals are transmitted by the layer 1 or the physical layer of ISO OSI reference model. So you may be knowing the ISO OSI, the 7-layer model. The bottommost layer is the physical layer. So physical layer, uh, or it is called as layer 1, that is responsible for transmitting the uh, signal from this from source to the destination. Okay. And what is a signal? A signal is basically a function of time and location. Signal is basically a function of time and location. So this is how a wireless signal is defined. And typically the radio transmissions are periodic signals. The radio transmission signals are periodic signals. That is, they are normally a sine wave. It looks like a sine wave. If you take an analog signals are continuous in nature. That is, they are continuous in time and their values are also continuous. It is, they never stop. For every millisecond, every nanosecond, some data will be transmitted. So the time is also continuous and the data or the values are also continuous. Whereas if you take a digital signal, it is discrete in time and its value also discrete. Okay, there is some definition like first for, at time 0, what is the value of the signal? At time 1, what is the value of the signal? At time 2, what is the value of the signal? Okay, there is discrete points we have. There is nothing like 1.5. At 1.5, what is the value? There is no value. Just we connect 1 and 2. At 1, what is the value? At 2, what is the value? That will be connected. Okay. So such signals are called as digital signal, which is discrete in time and discrete in values, and it has discrete values. So the general function of the sine wave is is given mathematically like this: g of t is equal to at into sine 2 pi f f subscript t into t plus phi of t. So here you can see there are three terms: a, f, and phi. A represents the amplitude of the signal, and f represents the frequency of the signal, and phi represents the phase of the signal. And with f, with a, f, and phi, there is a subscript t. There is an a subscript t, f subscript t, and phi subscript t, which means that amplitude changes with respect to time. A subscript t means amplitude changes with respect to time. F subscript t means frequency of the signal also changes with respect to time. And phi subscript t means the phase of the signal also changes with respect to time. Okay. So if you take a typical analog signal, sine wave, it will be looking like this. It will be like looking like this. Okay. So x-axis is nothing but time. Here x-axis is time and y-axis is the frequency. Okay. So sorry, y-axis is amplitude. X-axis is time, y-axis is amplitude. So normally amplitude represents the voltage of the signal. Normally amplitude represents the voltage of the signal. So this is nothing but the voltage at this point of time. The amplitude or the voltage of the signal is this much. Okay. Similarly, at this point of time, the amplitude or the voltage of the signal is this much, like this. Okay. And this is the frequency of the signal. This is nothing but the frequency of the signal. There is one. This is one cycle. One cycle. What is the duration? That is the frequency. Okay. And phi is the at what at at what angle the signal is starting. So that is called as phi. Okay. It is the phase of the signal. Phi represents the phase of the signal. Okay. Yes. So this just now we have discussed. Yeah. So any, so basically any periodic signal can be represented by using the Fourier representation, and this is that is given something like this. Any periodic signal can be represented in terms of uh, in terms of in terms of Fourier equation with a combination of sine and cosine waves. Okay. So basically it is possible to construct every periodic signal G, okay, by using sine and cosine. Okay, and that is given by Fourier as this equation: G of t is equal to 1 by 2 C plus sigma n equal to 1 to infinity a n sine 2 pi n ft plus sigma n equal to 1 to infinity bn cos 2 pi n ft. Okay, so here C represents the direct current, DC direct current, and an and bn represents the amplitude of the nth sine and cosine function. An and bn represents the amplitude of the nth sine and cosine function. Okay, so basically this equation, what it says in the sense, an infinite number of sine and cosine function is needed. Okay, an infinite number of sine and cosine function is needed, because you can see this particular equation, it is going from n equal to 1 to infinity. This also it is going from n equal to 1 to infinity. So we are basically discussing here how to construct a periodic signal. So to construct a periodic signal, you need an infinite number of sine and cosine function is needed to create an arbitrary periodic signal. To create an arbitrary periodic signal. Okay, but in real time, if you see the bandwidth of the medium through which the signal is passed, okay, the bandwidth of the medium through which the signal is passed. So signal is passed through what? Signal is passed either through air or cable or any other transmitter. The bandwidth of this medium is limited. So it has a limited bandwidth. It is not that it can pass any bandwidth. Here you can see f, the frequency f is multiplied with n. So what happens? What happens in the sense, as n approaches infinity, the frequency will keep on, the value of the frequency will keep on increase. Okay, here I don't say that frequency will increase, because if frequency, uh, yeah, the value of the frequency will keep on increase. As a result, not but the medium through which the signal is passed, it has a limited bandwidth. So basically it cannot allow all bandwidth uh, to pass. Okay, so 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 from this, what we can infer in the sense, it is not required, to actually create an arbitrary periodic signal, because in reality that is not required, because in reality itself your medium has a limited bandwidth. Okay, so therefore it is enough to consider a limited number of cosine and sine and cosine function to construct periodic function. You need not consider infinite number of sine and cosine function to create a periodic signal. Okay, so this is how an ideal periodic signal looks like, and this is a and this is a, what you call a sine wave with different frequencies. Okay, with different frequencies. So in real time also you cannot create a signal with infinite frequencies. Even though if you create a signal, the medium will not accept all the frequencies. Okay, right? So basically, a sine wave can be represented in time domain. There are three ways of representing sine wave. Okay, so that we will be discussing now. The first way is to represent in the time domain. In the time domain, the sine wave can be represented something like this. So here the x-axis is time, and the y-axis represents the amplitude of the signal. Y-axis represents the amplitude of the signal. So amplitude or voltage. A is amplitude and V is the voltage. So this is the signal. Okay, so this is the signal, right? So initially this is one signal and this is another signal. The difference is this signal is shifted. The second signal, which is marked in rose color, is shifted in phase. Okay, it is shifted in phase by certain degrees. It is shifted in phase by certain degree. How much it is shifted means this much it is shifted. Okay, whereas the first signal, you can see it is passing the origin. It is passing the origin. The second signal is not passing the origin. It is passing somewhere here. Okay, so that point, the difference between origin and that point is the degree of shift. So how much shift, that much that second signal is phase shifted. Okay, so this is the first way. This is the normal way to represent a sine wave. Here we represent the signal in the time domain, and The y-axis represents the amplitude, x-axis represents the time, and this is nothing but the frequency of the signal. Okay, one cycle. For one cycle, uh, what is the time? Okay, what is the frequency is nothing but 1 by t. Frequency is given by frequency is 1 by t. Okay, so for one cycle, how much time it takes? So if for one cycle it takes x amount of time, then the frequency of this signal is 1 by x. The frequency of this signal is 1 by x. Okay, fine. So this signal shows that the frequency is similar for all cycle. The frequency is similar, but in reality it need not be like that. Okay, the frequency of the signal may vary with time. Fine. So this is the signal in time domain, sine wave in time domain. So sometimes representing the signal in time domain may be problematic. Sometimes representing the signal in time domain may be problematic, especially if the signal contains many frequencies, especially if the signal contains different frequencies. In such cases, the signal can be represented in frequency domain. In such cases, the signal can be represented in frequency domain. Okay. So let us discuss how the signal will look like in frequency domain. And, and if you want to display the various frequencies, there is a tool, and that tool is called a spectrum analyzer. Using spectral analyzer, you can visualize the various frequencies of a sine wave or any signal. And there is a mathematical tool that is available for translating a signal from time domain to frequency domain is Fourier transform. Fourier transform is the mathematical tool using which a signal can be translated from time domain to frequency domain. Okay, so so sorry. So this is how the signal will look in the uh, frequency domain. So this particular diagram shows how the signal will look in the frequency domain. So here x-axis is frequency and y-axis is amplitude or voltage. X-axis is frequencies and y-axis is amplitude or voltage. So here you can see there is only one line. There is only one line because this is a periodic signal with a with only one frequency. It does not have different frequency. There is different cycle here does not have different frequencies. If there are different frequencies, then you may have uh, a different multiple lines. Okay, so here, so in this case there is only one frequency. Okay, so you are getting only one line. Okay, so as there is only one frequency, only so the figure only shows one peak. Okay, and the signal consists only a single part of only a single frequency part, right? But an arbitrary periodic function would have many peaks. Okay, right? So this is how the signals are represented in frequency domain. And the third way of representing the signal is in the phase domain. In the phase domain. So when you represent the signal in the phase domain, it is also called as phase state. The signal that is represented in the phase domain is also called as phase state, or the diagram to represent that it is also called as signal constellation diagram. It is otherwise called a signal constellation diagram. So let us see the diagram first. So this is how the signal is represented in the phase domain. Okay. So here you can see there is a basically there are three vectors were given. So this is one vector. This is one vector. This is another vector. Okay, and this is another vector. So the signal is represented in different phases. So this is the normal signal which is passing through the origin. This is the normal signal which is passing through the origin. Okay, so in this case it is called as it is called as in phase signal. It is called as in phase signal, and this is the case the signal is phase shifted by 90 degrees. The signal is phase shifted by 90 degrees. So here in this case, if the signal is phase shifted by 90 degrees, it is called as quadrature signal, Q. Okay. So here the signal is shifted by 45 degrees. Like that, you can represent how much the signal is shifted. If the signal is not at all shifted, then the signal will be just represented in the x-axis a line, okay, with an arrow. So this length of this line represents the amplitude of the signal. Okay, the length of this line represents the amplitude of the signal. And if the signal is shifted by 45 degree, it will be like this. If it is 30 degree, it will be somewhere here. If it is 90 degree, it will be here. Okay. If the signal is not at all shifted, if it is passing through the origin, then it is called as in phase signal. And the signal, the x-axis represents the phase of the signal. So here the phase is 0. Okay, the signal is represented by 90 degrees. Then the then this vector will lie on the y-axis. Then the vector will lie on the y-axis, and that is called as quadrature, right? So that is what is being explained here. So the length of the vector represents the amplitude of the signal, and uh, the angle is nothing but a phase shift. And if the signal is in line with x-axis, so if the signal is in line with x-axis, then it is called as phase 0. So that is otherwise called as in phase. That is, the signal is not at all shifted. If the signal is shifted by 90 degree, then that is called as quadrature. And that is called as quadrature, which is represented as Q. Okay, it is represented as Q over here, right? So this is about the various. Uh, this is how this. So this is about the signals of wireless communication, right? Fine. Okay. So let us stop here and continue from the next topic in the next lecture. Thank you.